part, we're going to do two sample means, the difference of two means, essentially. So very similar to two samples with proportions. The standard deviation is, of course, the Pythagorean theorem. So you notice these formulas look very similar to the single. They just have twice as much, the difference of basically. One thing to keep in mind is the degrees of freedom here. It's called the Welch rule. I used to call it the jelly rule when I did stats back in the day, because, you know, Welch jelly. So you use this big formula here if they're independent. We'll do the dependent versions next week, essentially. Okay. All right. And of course, we're still using t because we don't know the population standard deviation. We just know the sample. And the data must be obviously randomized and independent. All right, so researchers investigated into visual cues, effects of consuming food to two test groups are eating soup. One gets a regular size bowl, one gets an oversized bowl. So two different size bowls, basically. Each group can eat as much as they desire. They refill. If needed, the amount of soup is given in ounces, right? So basically, is there a difference when you have a different size bowl, essentially? So you want a 95% confidence interval. Okay. So if we're going to do that, we're going to need to figure out the standard deviation and the mean for each of these. So I'm going to copy this, copy to a tab 3. So let's go to tab 3, part 3, and we'll paste the values only, right? We can probably just move these all in one line, right? Okay, there we go. There's the first data set. So that first data set is the regular bowl. So this will be the oversized. Right, so we'll copy these ones. Copy, and then we'll paste that there with values only. We don't want that, that fancy formatting. Oh, didn't I overlapped it by accident there? There we go. Yeah, I don't know what's going on with that. Just replace it, yes. Okay, so it looks like in both cases we have 27 values. So we want the mean of the regular, the standard deviation of the regular, the mean of the oversized, is it? I think it's, we'll call it oversized. I don't know what it's called really. And the standard deviation of the oversized. Okay, we'll block these together. What's going on here? Where is the block? Oh, there it is. Block. 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 And block. Alright, we'll set these to the right. Alright, so equals the sum of all of those, right? Add them up. And divide by 27 values. There's our mean, and then sum. Add them up. Oh, okay, that probably still works. Divide by 27. Yeah, that works. Okay, and then the, oh, that's the wrong one. Crap. Let's take that and put that there. Okay, sorry. So let's do standard deviation here. So standard deviation dot sample. Highlight all those. And standard deviation dot sample. Highlight these ones. Close paren. What is going on here? Get bigger maybe? What is the issue? Standard deviation dot. Oh, I didn't put the EV. That's why. EV. EV. If you notice, as you start typing, it'll actually tell you what to type, or you can just click on it and it does it automatically for you. All right. Okay, so there's my values there, which I can translate over and figure out my standard error now, basically. You can get more or less values, but I think what we have there is probably fine. Okay, so what we have here is regular. All right, that was about 6.1 ounces. And the mean of the regular, oh, that's not what I want. There we go, sub-regular. Okay, it was 8.5 ounces. Alright, so I'm going to copy this, copy, paste, oversized, oversized, oversized. I think it was 8.4, wasn't it? 8.4, 14.7. Okay. 8.4 and 14.7. Okay, I think we're good there. Let's. Alright. Don't like the spacing. I don't know what's going on there, but nonetheless looks pretty good, right? So we'll copy the formula up here. Alright, we'll copy this. And we'll put it in there. Alright, so this is oversized minus regular. Right? Yeah, because oversized is more than the regular, so I give you a positive value. If you flip the other way around, it'd be a negative. Okay, so the standard deviation of oversized, regular, oversized, regular. Okay, so we'll copy that, copy, paste. So this is, get rid of this crap, 6.1 squared. Oh, I think I got that backwards actually. 8.4, sorry. Not that it'll matter, but just to keep the wording consistent. So this is the 6.1 squared. And then these are both 27, right? There's 27 values for both sets. Okay, that'll give us some value. Who knows? Then we need degrees of freedom after that, right? So our degrees of freedom is this Welch formula here, right? So we're going to copy that. Paste that there. Right, and we can put the wording in if we want. Oversized, oversized, regular, regular, oversized, oversized, regular, oversized. No, that's regular. Crap, what am I doing? Regular, regular, regular. Regular. This is regular. Oversized. Right? Okay. So obviously we put these in the computer. Right? That's going to be the same as this here. So I'm just going to copy that. Paste over that. Right? I'm going to copy this. Paste over that. Copy this. Paste over that. And this is 27, and that is 27. Okay, so that's going to give us an approximate value there. All right, so we need to get the standard error and the degrees of freedom from our spreadsheet. And then we can do our confidence interval. Okay, so we stop there for now. Let's go to our spreadsheet. We can copy these two to there, you know what I'm saying? We could take this, you know what I'm saying, copy. We don't have to do this just for visual sakes. Probably copy the whole thing actually. Okay, just so we can see it. Okay, so we'll do standard error here and the degrees of freedom here. Okay, so the standard error equals the square root parentheses with two fractions. So the first fraction is was it 8.4 or 8.5? Was I getting it wrong the whole time? No, 8.4. What am I doing? Wrong thing. Squared divided by 27, close paren, plus the other fraction, 6.1 squared divided by 27, close the parenthesis, close. So there's my standard error, right? 1.99. That sounds good. Okay, so degrees of freedom, this one's going to be tough. So, you know what, let's just do it. So equals, all right, numerator. So what I really have is the standard error squared. Okay, because that's what this piece is right here, essentially. Oh no, it's not, because the square root you have to get rid of, so I can't really do that. All right, so I have to kind of recreate the wheel here. All right, so we'll do it again. So the oversized squared divided by 27, close paren, plus the regular squared divided by 27, close paren, squared. All right, so that's this piece up here, right, which is the numerator. Now we have the denominator, so we have a couple different pieces here. All right, so the first part is 1 divided by 26, right, because it's really the 27, times, right, and then we got to do the oversized squared divided by 27, and then square that, right, and then we have the second part over here, right, which is this piece here. Again, 1 divided by 26, right, because it's 1 minus, times, and then regular squared divided by 27, and then that piece is squared, and then close paren for the entire denominator, right? See how that kind of lights up, right? When you click on it, see how it lights up, beginning and end, so you know the whole denominator's in there basically. Okay, so that is my degrees of freedom essentially. All right, so let's go back to here, right? So we got 1.99 dot dot dot. Wasn't it 1.99? 1.978, I guess. We'll just put a couple more numbers in there. Doesn't really matter. And this is 47.455, I believe, right? Yeah, close enough. Okay. So now we can do our confidence interval essentially. So let's go back up to here. And you know, these are both the same thing, but one's already filled out. So we already have this. So I'm just going to take the first part. Right? Copy. And paste. So that's our confidence interval. Right? So this is obviously oversized and regular. Oversized and regular. Okay, so we'll take this, copy, paste, change that to a plus. Right? Alright, so the difference in the two means, so basically 14.7 minus 8.5. Those are the means we have up here, right? 14.785. Minus a t-value, which we don't have yet. Copy. And the standard error was 1.9978 dot dot dot, right? Copy, paste, copy, paste, and change that to a plus. All right, so we just need the t-value essentially, right? That's the one thing we don't have. Okay. So t is going to be t dot inverse parentheses. All right, so we need to know, what is this? This is supposed to be, if we go back up to here, it's supposed to be a 95% confidence, which means 5% not confident, so half that's 2.5, so that's 97.5. Okay. So we're going to have 0.975, comma, degrees of freedom, right? That's going to give us some kind of t-value, essentially, right? Okay, so let's go back to our spreadsheet. So our t is t dot inverse, right? 0.975, comma, degrees of freedom. We don't need a -1 or anything like that here. It's already been calculated into the formula. Okay, it's actually right there, the -1. All right, so there is our t-value, essentially, right? So all we need to know, since we know the t-value now, just figure out the confidence interval, right? All right, so let's figure out the confidence interval. So let's just do that right here. So equals parentheses, mean minus mean, right? Sample minus sample, minus the t-value, times the standard error, actually, right? Then I can copy that, and paste that, make that a plus, and we get our two numbers, basically. All right, so 2.18, 10.21-ish. So essentially, 2.113 dot dot dot, copy this. Oh, I shouldn't have, that's wrong. We'll fix that. Oversized, regular. Okay, and this one was 10.287 dot dot dot, and these are in ounces. Okay, so there's our confidence interval right there. Let's double check. 10.219, 219, sorry, 219. I don't know what I was looking at. 19, 180. Boy, I don't know what I was looking at. Okay, here we go. Good enough. All right, so in context, we are, this is 95%, right? 95% confident the true difference in mean between an oversized bowl consumption and regular bowl consumption falls within the confidence interval, right? So we're 95% sure the true mean of the difference between people who get a regular size bowl versus oversized, that true difference in mean is in there, which means there is a difference, it looks like, between 2 and 10 ounces. You're going to consume more on the regular one. So would it be wrong to do regular minus oversized? No, it would not. So if I switched everything here to regular minus oversized, what would happen is these would be negative values down here, correct? So it would be -2 to -10 the other way, essentially, is what would happen. So neither one is really wrong, essentially. What would change is your in-context basic statement, right? Okay, so that's our confidence interval. So let's take another question here. Let's say you amount you charge friends for lawn care. Do you want to know if it's you're more likely to give a different price to someone that's a friend versus a stranger? So I have two different values, sets of data here. Okay. All right. So rename part 3, we'll call that one B. How does that sound, right? And we'll call this one A. Rename A. Rename B. Okay, that sounds good. All right, so let's copy that data over. So I'm going to take the data for friend. Why is it, I don't want Copilot. No, thank you. Copy. There's my friend data. Put that all in one column. And stranger. In another column. Okay, so we clearly have different n values here, which is fine. Okay, so mean for friend, standard deviation for friend, n for friend, mean for stranger, standard deviation for stranger, and then n for stranger. Okay. Okay, so add them up. The sum of all the friends, and divide that by 8, and then standard deviation dot sample for the friends, and that's clearly 8, and then the sum of the strangers divided by 7, standard deviation dot sample of the strangers, and that's 7. All right, so here's our base values that we need to do a hypothesis test. Okay, so now we can go back to here and do our hypothesis test to figure out, is there actually a difference in what we charge friends and strangers or versus strangers? Right, so this is, all right, we'll say step 1. What are we doing? So this is a, so the parameter of interest, we're doing mean now, right? Mean is the difference in the price for lawn care services offered to a friend versus a stranger. Never completely happy in the wording on these, but it gets the point across. This will be a 2 sample, right? We did 2 sample proportions, 2 sample mean, 2 sample t-test, because we use t for means, because we don't know the population standard deviation, for the mean difference in the price for lawn care services offered to friends, to friend versus a stranger. Let me see, you don't spell services, so no, typo. Okay, so we'll do our hypotheses. So H sub 0, H sub A, right? So you always assume equal. So mean sub friend equals, I don't know if this is the right way or not, but we'll go with it. It might be the other way around. It doesn't really matter all that much though, versus stranger, right? So it's always equal, right? Because essentially what you're really saying, if you think about it, thus minus equals 0, right? Because it's always equals 0 or equals something. So there is no difference is what the default basically is. So if I copy this, copy, We think there is a difference. We're not saying more or less, though, right? We're just saying there is a difference. We could change the problem and say we're charging them less, so it is not equal to 0. So this is going to be a two-tailed test, essentially. Okay, so that's what we're doing. Step 2. Can we do it? All right, so the mean for the friend, we got to get that. Sub f, I believe that was 281.875. Let me double check. 281.875, yep. And then we get the standard deviation of the friend. Let's 18.31. Right? Yep, close enough. And then copy, paste. This is approximate. We can, these never work out nicely. All right, so this was 211 point. Oh wow, this goes on forever, huh? Well, I guess it doesn't go on forever. We'll approximate it. Let's say 4285. 4285 dot dot dot. Okay. We're going to use the exact amount, but that's fine. And this, these were stranger. Unfortunately, it's 2 S's, but what are you going to do? All right, and 46.4322. Right, and we have the number for the number of values for the stranger was 7. Let's take this and go down, and then the number for the friend was 8. Friend was 8. Okay, so that's the basis of what we're doing. Okay, so the mean of the samples for the sample mean, x minus x. All right, we'll put a little bar above that, the difference in means. Should be 0, right? Should be, if they're the same. Okay, so if I do the standard deviation, thus the standard error of the difference of the means. And you can do little subscripts if you want, right? Maybe we'll add them in after. Okay, so that'd be the square root, and I got to put the 18.3.31 squared. That's 8, right? And then plus another ratio, 46.43 squared over 7. Okay. So if we want to do the subscript to be what? Friend and stranger, I think. Hopefully I got that in the right order. Sub stranger, 18.31's friend. Yeah, that makes sense. Friend, that's stranger. Okay. All right. So if I analyze what I have here, these samples are likely independent because you cannot be charged twice as a person, and you cannot be both a friend and a stranger, right? So clearly they're independently selected, and one does have nothing to do with the other. All right, so the data appears unimodal and normal when you create a histogram. So if you graph it, you'll notice it's fairly normal. It's not some kind of weird distribution. Step 3. Okay, what we're doing, can we do it? Now let's actually do it. Okay, so if I actually do it now, the mean of a friend right, so this would be sub friend, friend, sub stranger, right? So it would be the 281.755 minus the 211.43 dot dot dot, right? So that's about 70.45-ish, right? Like approximately, or maybe it's exact. Let's take a look. All right, so this one minus this one, yeah, well, 4 or 5 is close enough. Okay, and then we have to do the t. Let's go down to here. So t is equal to, let's deal the formula. It's right there. Copy. Okay, we do the formula because obviously when you do hypothesis testing, you know the population answer, so you can calculate t this way, not in the computer with the estimation of the model. Okay, so we have the 70.45 minus 0 because the difference should be 0, right? And the standard error, we don't know. We're just going to leave it as standard error, right? Okay. And approximates. This is where we go to the computer now, right? Okay, so we're going to put the standard error in and get our t. Okay, so we need standard error, and then we need t. Okay, so the standard error, right, is the square root, right? And then we have to do 2 fractions, correct? So the first fraction is the friend squared divided by 8 plus the second fraction, which is the stranger squared divided by 7, close parenthesis, close parenthesis. All right, there's my standard error, right? And then my t value, that one's going to be, well, basically it's going to be this mean minus 0 in the numerator, right? Expected minus, I'm sorry, observed minus expected, divided by the standard error, right? Okay. You can paste that in there if you want, right? So essentially that's what we did. Difference in mean, 0, divided by standard error. Standard error is right there. Okay. We have to do degrees of freedom now. Degrees of freedom. Ooh, that's going to be a bear. So if you remember the formula, if you don't remember, that's fine. What did we get for t, by the way? We got 3.766, 3.766, dot, dot, dot. That really doesn't matter, though. Okay, we need the degrees of freedom. Okay, so approximately. Okay. All right, well, we got a big formula. Let's go up here and copy it. It's the Welch formula, right? The old grape jelly one, as I like to call it. So I'm going to put that in the spreadsheet. Okay, that's right there, right? Move that up, move that up. Okay, so numerator has 2 fractions. So standard deviation squared divided by n, right? Plus the other fraction in the numerator, stranger squared divided by 7. And then close the whole thing and square it, right? So that's my numerator. All right, denominator, so divided by, okay, so the first fraction is 1 divided by 7, right? Because 8 minus 1 is 7, times, right? Then you have the friend squared divided by Oh crap, that's the wrong number. That should be E2, right? Do a deviation right there. What did I do? Oh, I might have done that twice. That should be E2, right? This should be deviation, not mean. I don't know why I clicked the mean. All right, so deviation divided by this, right? Square it plus the other fraction, right? All right, so that should be 1 divided by 6, right? Because you remember this is 7, so 1 minus that's 6. And then the standard deviation, oh, I might have messed up again. Standard deviation squared divided by 7, and then square that, and close paren. All right, where did I mess up here? I used E4 somewhere. Where's E4? I don't see E4, but why is it lit up? Oh, it's right there. That should have been E5, right? Right, because we're using standard deviations and means. I must have clicked the wrong one by accident there. Okay. All right, so 6.62. Let's just double check this if it's correct. All right, so we have I square the friend divided by 8, right? Plus I square the stranger divided by 7 squared, right? I wonder if an extra set of parentheses here makes a difference or not, just for argument's sakes. No, does not. Makes no difference. Right, and the entire denominator, right? See that parenthesis goes to there. That's the entire denominator. So 1/7 times friends squared. We can square the individual ones too. Plus 1/6 times. I think we're good. Okay, I like it. All right, so there's our goodies right there that we need. All right, so we got for an answer for degrees of freedom, what? 6.6? So, 6.6 something, right? 29, da 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 da. Okay, so we need our area now. Area equals 2 times t dot distribution. So the question is, why is it 2? Well, first off, let's talk about it this way. Okay, so this is a not equal to case, so it's a 2-tail, right? Come on, let's draw. Right, this is a 2-tail. So we have a t value right here. That's all the way over here, correct? So we want the area up here, correct? So the problem is, this is the 2-tail, it's the second tail, which is why I have to multiply it by 2. But the problem is, if I'm doing this t value, it's going to be all the area left to right. But if I want this, I got to do the 1 minus, don't I? Okay, so the first thing I got to do is 1 minus, put that in parentheses, okay? So I'm going to put in the t value that we found, comma, degrees of freedom, comma, true, right? And that'll give us our area. Because if I just did this, that would just be the upper part and not both parts of the curve. And it's a 2-tail. Why do I know it's a 2-tail? Because it's a not equal to, right? Could be more or less than we think. Okay, so let's go to here. We'll type in area equals 2 times, parentheses, 1 minus t dot distribution. Right? I'm going to click on the t value, at least try to, comma, degrees of freedom, comma, true. Right, what did we do here? Oh, I didn't close parenthesis, that's why. Right, so close parenthesis on that. There we go, so we get that value there. Okay, so about 0.009 and some change, 0.009. 0.009 dot dot dot. Either way, there's some more decimals after that, but they don't really matter, to be honest. Okay. Okay. Then we're going to go to step 4. Bold. Right. Oh yeah, because this is the p-value, right? P-value. Okay. So, conclusion, right? What we're doing, can we do it? Do it, and then conclusion. So the p-value is less than alpha, which is 0.05, right? So we should reject the null hypothesis, right? Because again, if it doesn't say in the problem what alpha to use, then you use the 5%, which is the Fisher rule, the 1 out of 20, essentially. Okay, so that means our sample mean is significant, means it's in the shaded region, and not likely to occur. Because if it's a very likely sample, then you can just ignore it. We got expected outcome. There is enough evidence to reject the null hypothesis. So in context, it is likely that that there is a difference in charge for lawn care services between friends and strangers. Because the default is there's none, so in context that there is, right? So if there is an error, then it is a type 1 error because we rejected the null hypothesis. Okay, so if we didn't do it, if we didn't reject it, then would have been a problem, right? Would have been probable type 2. Okay. So, however, the p value is very low compared to alpha, and the hypothesized value is, well, the hypothesized value would be 0, the difference, right? And did we do the confidence interval? We didn't, right? So the question is, would it be in the confidence interval or not? So is probably not in the confidence interval. Okay, but since it's very low, it's probably not going to be a type 1 error, but that's all we know essentially. Okay, all right.